Hello and welcome to HSC's second online lesson. Today we'll be talking about LEDs. So first off, what are LEDs? LED is an acronym for light emitting diodes. To the right are the parts of a conventional LED. The flat bottom surfaces of the anvil and post make up the lead frame that are embedded inside the epoxy lens/case to act as anchors to prevent the conductors from being forcefully pulled out, as well as making the LED different colors and enhance the brightness. The electronic symbol for the LED is below. The left side is the anode, and the electric current runs through to the right sides, the cathode. You can pause this presentation if you wish to examine the parts of the LED in the diagram. So now we're moving on to the history of LEDs. Electroluminescence as a phenomenon was discovered first in 1907 by British experimenter H.J. Round of Marconi Labs using a crystal of silicon carbide and a cat's whisker detector. However, not much was done after the discovery of the phenomenon until Russian inventor Oleg Lusev reported the creation of the first LED in 1927. His research was distributed to Soviet, German, and British scientific journals, but no practical use was made from the discovery for several decades. More improvements to the LED followed, and in 1962, the first visible spectrum LED was developed by Nick Holonyak Jr. while working at General Electric. So the first commercial visible wavelength LEDs were commonly used as replacements for incandescent and neon indicator lamps in 7-segment displays, first in expensive equipment such as laboratory and electronics test equipment, and then later in appliances such as calculators, TVs, radios, telephones, and watches. Until 1968, visible and infrared LEDs were extremely costly, around $200 per unit, so it had very little practical use. Hewlett-Packard was engaged in research and development on practical LEDs between 1962 and 1968. At the same time, HP and Monsanto organizations launched a collaboration into developing usable LED products. The first usable LED product was HP's LED display and Monsanto LED's indicator lamp, both launched in 1968. The early red LEDs were bright enough only to use as indicators, as the light output was not enough to illuminate an area. Readouts in a calculator were so small that plastic lenses were built over each digit to make them legible. Later, other colors became widely available and appeared in appliances and equipment. Now we're moving on to resistors. So what are resistors exactly? A resistor is a passive two-terminal electrical component that implements electrical resistance as a circuit element. In electronic circuits, resistors are also used to reduce the current flow, adjust signal levels, and to divide voltages, among other various uses. So what goes on inside a resistor? If you break open a resistor and scratch off the outer coating of the insulating paint, you might see an insulating ceramic rod running through the middle with a copper wire wrapped around the outside. A resistor like this is described as a wire wound. The number of copper turns controls the resistance very precisely. The more copper turns, the thinner the copper, the higher the resistance. In smaller value resistors designed for lower power circuits, the copper winding is replaced with a spiral pattern of carbon. Resistors like this are much cheaper to make and called carbon film. Generally, wire-wound resistors are more precise and stable at higher operating temperatures. The electronic symbol for the resistors is shown as below. They do not have an anode and cathode side and can be interchanged. For part 1 of today's project, we're going to be making an LED and resistor circuit. So let's first take a look at this schematic. Remember how I showed you the symbols for the resistor and the LED before? This is exactly what it is, and this is a battery. So the electrical current starts off with the plus, and then it runs through to the resistor where it lowers the voltage, and then it goes to the LED, which emits light. After, the rest comes back into the battery. However, instead of a battery this time, we're using an Arduino. So the requirements for this project is an LED, an Arduino, jumper wires, and a resistor. Oh, and don't forget your breadboard too. If you want to try solving this by yourself, you can pause the video here and try to figure it out. So here is our physical representation of the Arduino and our breadboard schemata. So in this case, I'm going to go follow through with where the current runs through. It starts at the 13th pin, and power is provided by the Arduino to this wire. And first it goes through the resistor, and then it goes to the LED, goes through the anode, and comes out the cathode, and back into the ground. This completes the circuit. Now that you have finished your circuit, you would want to connect your Arduino to your computer using the blue cable provided by the Arduino toolkit that you have. After, please open up your sketchpad for Arduino called Arduino IDE. It should be on your computer if you have a Windows, and if not, it should be an online program that you could open up. So first off, we're going to let our program know what we have inserted into the Arduino, and on our case, on pin 13, we need the Arduino to provide energy. So we're going to let them know that we have integer LED at pin number 13. After, we're going to go to our setup. Will be pin modes LED output, and now this is declaring that this pin at number 13 is an output. And here is where we put our executable code. What we're going to do is digital write LED high, which turns the LED on. Now that you have done this, please verify. Save if you must. Now that we have done this, we could upload to our Arduino. And when it's done uploading, your LED should have been turned on. Once you finish with this, we could move on to our next and final project for this week. For our next project, we're making a traffic stop LED, which will consist of 3 different LEDs and a slightly more complicated programming. So let's first go through our electrical currents. So what we have here are 3 differences of energy from pin number 10 through 12. And what we're doing is each one provides electrical currents to each of the LEDs. Now, how this works is because they're from each of the different legs, if one gives energy and the others do not give energy, only number 10, which is connected to the green LED, will light up. Now, let's follow one of the LED currents to find out how it works. So number 10, it goes through this wire and it goes through the resistor to reduce the amount of voltage that's going to go to our LED. After this, it comes in through the anode, out through the cathode, and to our receiving line, which will come in back to the ground. Now the same logic applies for the rest of the LEDs, and we have a working circuit. So now we move on to programming. First, we have to declare our variables. These are going to store our data that we can reference throughout our code. Number 1, for example, the green variable represents the pin that the green LED is connected to. Now in our case, our green LED is connected to leg number 10. Our yellow one's at 11 and our red one is at 12. So you just have to set them up by keeping in mind which pins are which. Now we're going to write our delay functions. These ones are going to be how many seconds each color should be at for each LED. Now this time is in milliseconds, so we're going to want to put ours at, let's say, 5 seconds. That will be 5,000 milliseconds. For yellow, it stays at yellow in a traffic light for a less amount of time than green or red. Therefore, I'm going to make this 2 seconds. Now int red is going to be 5 seconds again. Now we're going to be moving on to our setup. We need to set up the pins so they act as an output and not an input for electrical voltages. The pin modes function accepts 2 parameters, the pin number first and then the mode separated by the commas. And calling an output declares that this is an output. Now I'm going to copy this and make it the same for yellow and red also. Now we're going to do our loop functions. The loop function creates a loop that the program will run through, so every time we call a function, it will turn a light on, and then we could set a delay so it doesn't change until that time stops. So there's multiple ways of doing this, but I'm going to make it as simple as possible. So digital write tells us at what power voltage we will be providing electrical energy to the wires. In this case, we're giving it to green, and it will be high. And then we're going to give a delay, so the green LED stays at high. And remember our delay function we have defined already at top as 5 seconds, therefore we just need to write delay green. Next, we're going to turn off the green light and then turn on the yellow light. So we're going to go back to our digital write function. And then green, comma, low, which is going to stop providing the electrical current that the LED needs to run. Next, we're going to turn on the yellow light. So yellow, and we're going to do high, which is turning it on. Now we have to put a delay in, and remember our delay again was defined here. Then now we turn it off like we did for the green. Now we repeat this again for our red. And with this, our code is finished. And now, again, we could upload it. Once you're done writing this code, you'll need to upload it to the Arduino using the USB cable that should have come with your kit. The light should start blinking in the pattern we have defined using the function calls and the delays. You should always test your Arduino by verifying your code with this button up here, and after sending it over by uploading it. If you have any questions about this, I will see you in tomorrow's chat. Have a nice day.